Our plan here is to do some more practice for your quiz on inverse trig. So the goal of question 1 was to check that you understand that on inverse functions we swap the x and the y. So look at what we know about the original function f. When we put 3 in for x, the result was 7. When we put 7 in for x, the result was 4. So we've got 2 ordered pairs. Only one of those will probably be useful to us, because look what our question is. On f inverse, what do we get when we put 7 in for the x coordinate? So which one is it going to pair up with? 7 for the x coordinate on f inverse pairs up with this point where we had 7 as the y coordinate on the original function. So if 3, 7 is on the original function, then 7, 3 is on the inverse function. So the second piece of given information was just to make you think about the problem. Okay, in number 2, I think we've discussed this in class several times now, that we know that inverse functions are a flip across the 45-degree line, but you are now going to remember its equation. It has a y-intercept of 0 and it has a slope of 1. So the line of reflection is y equals 1x. For example, we could put here our square root function and our squaring function so you can see what we mean by reflections across that diagonal line. Okay, a quick review again of our 3 inverse trig functions. So we need to have a good understanding of the original trig graphs. So the cosine graph has an amplitude of 1, and I'm going to choose this length as pi over 2 because pi over 2 is about 1.5. So remember that pi over 2 should have a longer length than your value of 1. So my value of pi here, if I extend my graph, so our cosine wave, remember what our cosine wave looks like. It hits its minimum at pi, and then it would continue, and it would continue in both directions. So for our 1-to-1 section of cosine, we're going to take a maximum to a minimum. So we're going to take our restricted region for cosine from 0 to pi, because if we want the inverse to be a function, not only does it have to pass the vertical line test, this will have to pass the horizontal line test, so that when we flip it, it will be a function. So notice our endpoints here, and it might be helpful. Make sure you know what you're flipping here. 0, 1 is going to be flipped, and this endpoint is at pi negative 1, and this point at pi over 2, 0. So let's flip each of those. Here's 0 pi over 2. Here's our point 1, 0. And if you didn't catch this in class, remember geometrically that reflections across any line, that line of reflection is a perpendicular bisector, so we go the same distance across that line. The same distance across that line. So that might be helpful if you find it difficult to graph these. So here's our point negative 1 pi. And now remember to give me a curve here. And notice that this point that is on the reflection line isn't going to go anywhere. So if you folded your paper, does it look like the purple graph would lie on top of the green? You don't have to be perfect, but have a graph where I can see that you've reflected them across the line y equals x. Our sine wave starts at 0 and increases, and it would continue over to 2 pi. So we're going to go backwards. We've got an amplitude of 1. So to get a 1-to-1 section of a sine wave, we don't want to go over any hills or valleys because then it wouldn't pass the horizontal line test. So a 1-to-1 section, we're going to take a minimum to a maximum. So here you can see that our restriction is negative pi over 2 to positive pi over 2. And again, we're going to fold across that 45-degree line, and my pen is a little thick here, so it might look like everything's on top of each other, but let me reflect this. And these points should be folded across this line. So here is our point 1 pi over 2. And here is our endpoint at negative 1, negative pi over 2. So this green curve is our inverse sine. So here's our graph, and I guess instead of y equals here, I called it g inverse of x is inverse sine of x. And our tangent graph is easier to do our restrictions because we know that every section of a tangent curve goes from a minimum to a maximum. But notice, unlike the others, that we go all the way down to negative infinity and up to positive infinity. Our asymptotes here, x equals negative pi over 2, x equals positive pi over 2 for our vertical asymptotes. And that's what we're going to choose as our restrictions. Do you see that it's the same as the restrictions for sine, from negative pi over 2 to positive pi over 2? And when we reflect this graph across the diagonal, what I think might be helpful for you is if you take the horizontal asymptotes and flip them first, so they will become horizontal asymptotes. And let me get some space here to label this. This would be y is equal to positive x over 2, and y is equal to negative pi over 2. And we flip across and put arrows. Our graph has to get very close to the asymptote, and it continues infinitely. So notice that on the original tangent function on our blue wave, so this blue curve is our h of x tangent function, its range is negative infinity to positive infinity. And what changes, this is our h inverse of x. Our arctangent function has a domain of negative infinity to positive infinity. So visually you should be able to do those reflections. You must remember the restrictions, because now look at how they come into play on these next problems. So what are you asked to do when I ask for the inverse sine of negative 1/2? Immediately you should be thinking that you have to stick between negative pi over 2 and positive pi over 2. We're looking for an angle that has a sine of negative 1/2, so I hope you're picturing the unit circle. And negative pi over 2 goes down through quadrant 4. Positive pi over 2 goes up through quadrant 1. So this angle has to be negative pi over 6. So in an inverse problem, you're given the ratio, you're looking for the angle. So we're working backwards. Here we want inverse cosine of negative radical 3 over 2. Remember, your restrictions for inverse cosine are 0 to pi. So now you're thinking the top part of the semicircle from 0 to pi. The negative radical 3 over 2, I hope that sounds like the long leg of a 30, 60, 90 triangle. So here's our angle of rotation, because we want the cosine to be negative square root of 3 over 2. So here we're going to come up with positive 5, 6 pi. So you need to know your unit circle. In number 9, arctangent. And I mentioned that I prefer these in their form before they were rationalized, because tangent is the y-coordinate, that's the vertical leg, to the x-coordinate, that is the horizontal leg. So this tells me that the x side is longer. So I know that where this comes from a 30, 60, 90, where I have 1/2 over 1/2 square root of 3. or square root of 3 over 2. And the halves have canceled. So you need to recognize that. We don't always want to go back to scratch. So for arctangent, again, we know that our restriction is negative pi over 2 to positive pi over 2. So in our unit circle, if we want the tangent to be negative, that tells me I'm down here in quadrant 4. And notice how I draw my 30, 60, 90. I want the short leg to be in the numerator, and I want the long leg to be in the denominator. So since tangent is y over x, I want the short leg to be my y coordinate and the long leg to be the x coordinate. So I know that I want this 30, 60, 90 triangle. And our angle here, I've almost used up all my space. This angle is, again, negative pi over 6 for our final answer. All right, in number 8, the trick here is that we're not actually looking for the angle. Once we draw a picture of this triangle, so step 1 we said was to draw this triangle, and then we don't care about the size of the angle, but we want to immediately in step 2, so step 1, draw a triangle, and then step 2, find the cosine of that angle. So these are just Pythagorean theorem questions. So let's see if I can draw a triangle that has an arc sine of negative 7 over 24. I recognize that as a Pythagorean triple, 7, 24, 25. Sine is opposite leg or vertical leg over hypotenuse. So I want to draw a triangle in quadrant 4 where the opposite leg, that's always vertical, is negative 7, and the hypotenuse, and I think I've got a mistake here in my problem. Let's fix this. I think that's my typo. Let's make that hypotenuse 25. So that it turns out I'm sure I wanted that to be a Pythagorean triple. So let's fix that to be 7, 24, 25. The 25 has to be the hypotenuse, since the hypotenuse has to be the longest side. So I'm sure I typed that problem incorrectly. Okay, so we've got our angle. What is its cosine? Step 2, what is its cosine? That would be the adjacent leg over the hypotenuse. So 24 over 25. Let me move that so it's not in the way of our next problem. So that's the cosine of our angle. We don't know the size of that angle. We don't care about the size of that angle. We just wanted to know the cosine of that angle. Okay, and then in question 9, it's 2 of question 8 put together. So let's see, I'm going to pause and draw those 2 triangles so you don't have to listen all the way through that. Okay, so how did I draw my triangles? I know that the definition of tangent by SOHCAHTOA is opposite leg over adjacent. So here I drew opposite leg 4 over adjacent leg 3. So we know our hypotenuse is 5. For the inverse sine, I know the definition from SOHCAHTOA is opposite leg over hypotenuse. So I drew a triangle that has an opposite leg of 12 and a hypotenuse of 13. So I know the adjacent leg is 5. So now we can go to our formula. So I'm going to take it right from this list. So I want to take cosine of A, cosine of B, minus sine of A, sine of B. And I'm going to read them right from the pictures above. So I paused the video to write those in since my video is getting a little long. But let's take a look. Cosine of A is adjacent over hypotenuse. Cosine of B is adjacent 5 over hypotenuse. Sine is opposite over hypotenuse, and sine of B is opposite over hypotenuse. So I multiply and they have a common denominator. So we come up with negative 33 over 65.